Welcome back to Manish Kumar channel. So today we are going to discuss about the complex analysis, why complex analysis is important. So if you know already in the real line, you know real numbers, right? Real line, right? 0, 1, 2, and so on, keep increasing, and similarly this. So it goes to plus infinity and it goes to minus infinity. But in complex analysis, the question is how many, infinities are there, right? So complex analysis, it means first we are going to work on the complex plane. Complex plane means you have this plane where x-axis and y-axis and iota minus iota towards positive direction of y and negative direction of y. Right, so you are going to write any point x comma y in complex plane x plus iy, right? So the natural question is how many infinities do we have in complex plane? So answer is only plus infinity. Only single infinity is there in complex plane. In the real line, you have two infinities, plus infinities, minus infinities. So this is very important basic difference between C and R. Also, in real line, you can say any x is, let's say x is this point and y is this point, right? So you can define an order. X is less than y. So real line is an ordered field, but in complex, you cannot. So in complex plane, you cannot define such order because of the fact that I square is equal to minus 1. Ordering means any non-zero element x, any non-zero element x, then its square. Its square is always positive. But this is not true in complex plane. If you take I, which is non-zero quantity, right? And if you do I square, it is not going to be greater than 0. So this violates the condition. This contradicts the condition of a greater than 0, right? So this is not an ordered field. So this is ordered and this is not ordered. So these are the two important ingredient we have seen while going to study with the complex analysis. It consists of only single infinity and it is not an ordered field, right? So let us move further. How we are going to claim that this complex and real analysis is just looks like a glass and clay type structure. So motivation, why complex analysis is more powerful. So in complex analysis, any function is one time differentiable, right? Derivative denotes the prime or derivative of function. If it is one time differentiable, then it is automatically infinitely differentiable. That is a very beautiful result in complex analysis, right? While in real analytic functions, we require a power series representation. You got my point on it? Another complex analysis exhibit beautiful properties such as Cauchy integral formula and residue theorem, conformal mapping that we will see in the course later on. And more importantly, many real integrals, right, such as improper integrals, becomes easier in complex plane. When we solve the improper integral in the real line, and then life becomes harder. So if you see here, the improper integrals minus infinity to infinity cosine x square plus 1 dx is equal to pi by e, or minus infinity to infinity 1 by x square plus 1 dx is pi. Using contour integration, life becomes easier and we get the direct result, which is much harder in real analysis. So that is another important property of studying complex analysis. And it is a powerful tool. Use contour integrations and residue theorem to simplify, real integrals, and compact and elegant theorems like Cauchy integral theorem, Leibniz theorems are deeper insights with minimal assumptions. Analytic continuation allows extending functions beyond their original domain. Harmonic functions and PDE, many solutions of physics problem, right? Uh, you must have encountered heat equation and wave equation in differential equations, right? Are naturally expressed in complex functions, right? The solutions are basically okay. And similarly, the conformal mapping is used for aerodynamics and many other fields. Some drawbacks, now we can compare with the real analysis. Why it is because of the fact that it's a complex in nature, so require more concept and such as analyticity and CR equations that we will see throughout the course later, and limited to holomorphic functions. But in real world, uh, real analysis, many functions are discontinuous even, and even non-differentiable functions are not holomorphic, right? So we cannot treat such functions in complex analysis. And there are some geometrical interpretations, right? So what is real analytic and complex analytic? A real analytic functions fx is called real analytic on an interval if it can be expressed as a convergent power series. Power series you have already studied, like Taylor series, Maclaurin series in your calculus 1. So you can just revisit your power series because it is going to be useful in this course. Okay, and in a neighborhood of every point in its domain, right? So power series is convergent, right? Convergent power series we can have for a given function. So example, if you see the function e power x is real analytic because we can always find the power series expansion of this, right? And this series about x equal to 0 is Maclaurin series actually. So which converges for all real x. So this function is real analytic. Okay, and in complex analytic, so analytic function, or sometimes people call it as holomorphic functions. So a function fz is complex analytic if it is differentiable in an open set in the complex plane, right? So key condition, it must satisfy CR equation. CR equation is simply, if your function is fz is like ux plus iv. So you can say that partial derivative of u and partial derivative of v with respect to x and y, and partial derivative of u with respect to y and partial derivative of v with respect to x with negative sign agrees. So these two equations are called CR equations. We will see later, right? So the function e power z is complex analytic because e power z equal to summation n equal to 0 to infinity z power n by factorial n. We can write always the expansion form, series form, right? Power series form. So which converges for all c as well. Okay. So here we have seen like a real analytic function can be extended to complex analytic. So when we say a real analytic is also a complex analytic, means if the power series remains valid to extend z as x plus iy, the function in the complex analytic, right? Or holomorphic. If it cannot be extended to holomorphically, then it is not a complex analytic. So many real functions which are real analytic but not complex analytic. So let us see one example. So is this function is complex analytic? E power x? Yes, power series is, we can write power series which converges. So also we can extend it to the complex numbers. Instead of x, we can write z x plus iy, and this power series is also valid for whole complex plane. So this is well defined and holomorphic for all of entire C. So the function e power x is both real analytic and complex analytic. Let us see as an counter example. The function fx 1 by 1 plus x square is real analytic, right? If you see the power series expansion for mod x less than 1, 1 upon 1 plus x square can be written as the power series. And since this power series converges for all x, so fx is real analytic, right? And the x ranges from -1 to 1. Now, what about this function is complex analytic or not? So answer is no. If you check analyticity on complex plane, so z 1 over 1 plus z square. So now this equation has solution. If you solve this equation, 1 plus z square equal to 0 when z equal to plus iota and minus iota. So this function is not analytic around I and minus I, right? So has singularities. So not holomorphic in any domain containing these points, right? That we will discuss singularities and other stuff while teaching the course, right? So key observations, what we have observed, the function can be real analytic where a power series expansion in R without being complex analytic, right? If you see this function, 1 upon 1 plus x square is real analytic since it has power series in R. However, this fails to be complex analytic because of the poles, right? And we preventing holomorphic extension to the entire complex plane, right? If we remove this pole, if you see this pole in the complex plane, 1 and this is -1, so this is iota basically minus iota, right? If you take any domain like this or any domain this or any other domain this outside from these pole, outside from these 2 points, if you take any domain containing these two singularities, so function is not real analytic at these 2 points. That is the meaning actually. Okay, if we avoid these poles and take our domain for this function, so this function is going to be complex analytic if we are excluding these 2 points minus iota and plus iota, right? Apart from any other domain which are not covering these two singularities. So here some real analytic functions fail to be complex analytic. This is the example. Now, as we discussed about the clay and glass. So clay means the clay. If you press locally, it changes its shape without affecting the whole structure. But in complex functions are just like a glass. If you change little bit locally in one place, so the whole glass structure will be broken, right? So this is just kind of rigid global perfection, but this is local changes and flexible real analysis function, right? So if you see function fx equal to mod x has sharp bend at x equal to 0, and clay failure, if you see the real analysis function fx equal to x power 3 by 2 sine 1 by x has no second derivative at x equal to 0. So if function is this function is first time differentiable, right? But in complex analysis, if a function is first time differentiable, then it is also automatically differentiable at infinite times. But this is not true in real case, right? This function is even not differentiable in second time, not differentiable in third time, and so on. So we require additional condition like power series need to be valid. For that, then we can able to go with the real analytic functions, right? And why this glass? Because integral enforces global smoothness like Cauchy integral, and we will see later those things. Now real versus complex fundamental differences, what we have learned now. So real analysis, limited derivatives, right? But in complex analysis, if once first derivative exists, all derivative will exist, right? Derivative of all order till infinity. This is the beauty of complex analysis. And power series rare, needs c infinity to represent the power series, but for this always exist because of the derivative exist for all order. So it should be it is analytic actually. And integration, so limited tool to solve the real world problem like improper integrals is much harder than complex analysis. So it uses Cauchy's theorem and residue theorem to solve the integral in a very fast and easy manner. And gloss analogy, so a single crack mismatch or shatters the whole functions, right? So final conclusion, in real analysis world, it function becomes clay. In complex analysis world, function becomes glass, flexible, rigid, local, global, messy, perfect, right? So complex differentiability is a superpower here. So thank you very much. Thanks a lot.